And our speaker, Mr. Mayank Mishra, is currently pursuing his PhD in physics from the University of Science, Education and Research, Kolkata, which is IIM Kolkata. He joined in 2023. He completed his MSc in physics from National Institute of Technology, Calicut, IIT Calicut, in 2021. His research interests include neutron star, black hole thermodynamics, and high energy physics. Apart from that, he is also interested in exploring spiritual knowledge from our age-old wisdom. So, as the doctor is he is always interested to know something that we cannot know anything about. So, black hole we are very interested to hear about.
Hello, good afternoon, everyone. So, as my topic is black hole information paradox, I would like to first of all give you the contents. So these are the contents. First one is introduction, then black holes, then physics of information, then Hawking Bekenstein radiation, then the paradox. What is the Hawking paradox? Then resolving the paradox. Then firewall. Then I will be going through conclusion and references. So first of all, what is black hole information paradox? First of all, what is black hole and information paradox? I think we all know. Paradox is in Hindi I can translate it for you as virodabhas, something which is self-contradictory in itself. So black holes. So let me introduce it in the following way. Black holes are supermassive objects in astrophysical objects, just like stars and planets, which are massive, but black holes are the results of dead stars, which are the results of dead stars, and they become supermassive, and their size becomes very big. Their size is reduced so much. That is why they become so much compact, and they are very much gravitating. Let me from this picture, you can see that this event horizon, this is called the boundary of black hole, and there is a singularity, which is at the center of black hole. We will come to that in a moment. But then after a black hole, we will go to information. So what is information? So any property of a physical system which is important as far as the physics we know, like anything we see around us. Let's suppose this thing, it has some mass, some charge, and other properties. It has its spectrum, through which we can know many of its chemical compositions, how through what it is made up of, and all the properties which can be studied. These are the information related to any physical object. So then we will talk about quantum information, which is different from the classical information, and quantum information is never lost. So we will go to that. So black holes, what is the special property? The most special property of black hole is that a black hole is something through which nothing can escape. Once something falls inside the black hole, it cannot come, because the escape velocity of, in a layman language, we can understand it in the following way: that if something go inside the black hole, then it needs the velocity greater than the speed of light to come out. Just like you know the escape velocity on Earth's surface also, anything, if you have to send it outside the Earth's surface, you need some escape velocity. In the same way, if something trapped inside black hole, if it has to be sent outside the black hole, you need the escape velocity, but that escape velocity is greater than the speed of light. And that is why, as we know that nothing can move faster than the speed of light, hence we cannot expect anything going inside to come outside. The next thing is the black hole is the reason through which, black hole is the reason through which there is a causal disconnection. What is causal disconnection? Is that anyone outside the black hole cannot see any event what are the events going inside the black hole? It is completely disconnected. It's any information cannot come. Just as we have said that even light cannot come. So anything inside you cannot see, because for something to be seen from inside, you need something to come, but nothing can come. Therefore, you cannot expect. Therefore, it is disconnected. So earlier it was thought that the black hole is a completely black thing. It has no radiation. Just like we know that if we have studied somewhat thermal physics, then we know that everything radiates. It has its own temperature, and because of its temperature, it radiates. But black hole cannot radiate. It was thought earlier. Before Hawking radiation came, that we discussed. So everything, so black hole has no temperature. And John Wheeler described that black hole has no air. It has only three properties: mass, charge, and spin. There is no more property as other objects have its temperature, its many other things that can be described of a black hole. Only three things can describe a black hole. These are mass, charge, and spin. This is the image of black hole. You can see there is singularity at the center. There is singularity at the center, and event horizon. Event horizon you can understand as the boundary of black hole. So physics of information, as we have already discussed, information. Now let us talk about quantum information and how is it different from classical information. So by quantum information, whenever I say, what we mean is that there is something called measurement, which is very important in quantum mechanics. So when we do measurement, that is not the quantum information that we need, but rather the wave function that we have prepared. So this is something, if you understand about quantum mechanics, then we can understand that by saying information in quantum mechanics, we understand the state that we have prepared, the wave function that we have prepared, and that is never lost. That is and why is it never lost? It is not lost because there is a time reversal symmetry. There is a time reversal symmetry for the Schrodinger equation. Schrodinger equation is the basic governing equation of the quantum mechanics. So this was all the classical thing. What is black hole? There was laws of classical mechanics, laws of black holes, laws of mechanics for black holes. And but then Wittgenstein was interested in 1972. Wittgenstein was interested in the thermodynamics of black holes. So he draws some analogies between black hole thermodynamics and black hole entropy and its area. Okay. And also one thing I wanted to mention, that area of black hole was thought to be only increasing in time. Because if anything fell inside, then its mass will increase, and mass was directly related to the area of black hole, radius of black hole. And we got the Schwarzschild black hole, radius equal to square. So radius and mass is directly related. So that is why if mass increases, then its radius will increase, which will in turn make the area to increase. But then in 1974, Hawking did some calculations around the event horizon using quantum field theory at the event horizon. And he described that if virtual particle is created at the event horizon, then it may happen that one will fall inside, as you can see there. One will fall inside the event horizon and the other will go outside the event horizon. In this way, there will be a radiation. As classically black holes area should not decrease. Now due to thermal radiation, area can decrease because I have described there is Hawking said that there will be thermodynamics of black hole and it has some temperature. That is why it will radiate, and due to radiation, its area will decrease. Now let me come to the paradox. What is the paradox? So classically, the information inside the black holes was well intact. It's classically before this Hawking radiation came, the information was inside the black hole. although the outside observer cannot observe it, बाहर वाले उसको observe नहीं कर सकते हैं, लेकिन information जो थी वो माना जाता था कि अंदर है। अब हम भले ही उसको चेक नहीं कर सकते कि अंदर क्या क्या गया है। अगर कोई चीज ब्लैक होल के अंदर गई है तो वो क्या गई है, इस चीज को बाहर वाले ऑब्जर्व नहीं कर सकते, लेकिन अंदर में है वो इंफॉर्मेशन है, ये पहले सोचा जाता था। This was the thought earlier. Now due to Hawking radiation, it will eventually evaporate. So eventually, slowly, due to Hawking radiation, the black hole's area will reduce, the size will reduce, and eventually it will evaporate. Means it will be completely gone, slowly shrinking. After that shrinking, the information that was inside the black hole, that is not remaining there. Suppose something went inside the black hole. What was the thing that went inside the black hole? That we cannot know. So this is something related to loss of information. But we know that quantum information cannot be lost. So this is the paradox. This is something self-contradictory. यही विरोधाभास है कि क्या अंदर ब्लैक होल के अंदर क्या गया था, इस चीज को हम लोग नहीं जान सकते हैं, क्योंकि हॉकिंग रेडिएशन से भी उस चीज का इंफॉर्मेशन नहीं आता है। तो वो जब एक बार ब्लैक होल खत्म हो गया, इवैपोरेट हो गया, क्योंकि कौन सा इनिशियल स्टेट क्या था इस बारे में हम पता नहीं लगा सकते हैं, वो फॉरएवर गॉन हो गई। तो this is the paradox. Now let me introduce something about how it was thought about resolving the paradox. So in 1992, Susskind proposed complementarity. So complementarity, what was it? Susskind proposed that the two observers inside the black hole and outside the black hole, they are causally disconnected. So you do not need to prepare the copy. So one thing I want to try to explain is that there is no closed theorem that if a copy of quantum information cannot be created. So due to which Susskind tried to solve the paradox in the following way. He proposed holographic principle. What is holographic principle? It was discussed day before yesterday. So holographic principle, let me explain in the simple language that all the degrees of freedom inside the bulb is related to the degrees of freedom on the boundary. So we can understand the physics inside the bulb is same as the physics on the boundary of that bulb. So whatever is the information inside the bulb is there also present on the surface, on the event horizon, and that is why it can be radiated in the form of Hawking radiation. So for the outside observer, the observer can observe the information due to the Hawking radiation, and this was the proposal of Susskind, and whoever is inside observer that can observe the information, that was never a problem. That was never nothing special there. So the complementarity requires holographic principle. Then there was a firewall. Just understand this much we can understand about firewall is that this is something which contradicted the complementarity in the following way that the three scientists came with the paper and they tried to explain that if someone tried to go inside the black hole, it will be burned up. Its temperature with the incoming observer will get so much heat up that it cannot go inside the black hole. So now let me just tell you the conclusion. So classically, the black holes keep information conserved, but after the paper of Stephen Hawking, that was not possible because ultimately the black hole is going to be evaporated. So there is a chance that the information that will inside the black hole will be lost. So Hawking's radiation led to the information paradox, and all the scientists tried to solve it, but they could not do it, as we have discussed the complementarity, which is yet not solved. So it is still a puzzle there that what happens to the black hole information and information loss. And and there is scientists are thinking in this way that if some quantum gravity theory comes up, then only it can be resolved. So these are the references. Thank you.